Hello, good morning. We will start our third session of our introduction to HPC. So today we will have a busy day. We will be covering two important elements that are crucial for using correctly an HPC cluster. So let's start with that right now. I think the schedule for today will be like this. I hope we can cover the main material for the submission of jobs, job scripts, interactive sessions, and job arrays up to around 10:30. We stop for a few minutes to drink some water, and we will be covering 10:45, something like that, for the second part, for the terminal multiplexer, which is another important thing when you start working with HPC cluster for real, for seriously. So let's start with this. Let me share the screen with you. So this is what I will be doing today. The material is here, so I will be starting from this. So I will be copying the link for you here on the chat. If you want to follow this on your own browser, it's right here. And I invite you to connect to Thorny. Everything that we will be doing will be, in a small portion, will be on the web interface, but I will also facilitate my interaction by opening the terminal here. So I will do this. See here, and in that case, I will share with you the link for Open on Demand. If you don't know it, is this. So I will be copying this here. So you click on the link, your browser will redirect you to the authentication page. You enter your password, username, password, do authentication, and you land on a web page like this, the dashboard. And from here, what I will be doing is I will be using some of the tools that I will be showing you. We'll create a new one, which is the terminal multiplexer, which gives me another good thing about this, is that preserves me this session. I hope a little bit, so I can go back and forth between this and the web page where I'm demonstrating the topics for today. So on the workshops hands-on, and I will be git remove. So you execute this command. If you don't have this, with the command git clone this, you can download all the materials for all the sessions, including the exercises and tutorials or examples that we will be presenting today. And I will be adding this to the chat. So now we have two links, and the third one is a command line that you will execute if you have not done so on the terminal here. That you can use this terminal that I opened inside Open on Demand, or as we mentioned in the very first session, you can have your own SSH client, your own way to access the cluster, and that's perfectly fine. As soon as you are inside the cluster, it means that you see something like this. You are in the cluster, and you inside, and you can operate the cluster as usual. So let's start with this. I introduced this with a mental experiment. All right, let's call it that way. and that I introduce different elements of complexity little by little. So this is the idea. Imagine you have your own computer, the computer that is in front of you. It's all that you have. And you need to run a simulation. Big, heavy model or simulation or large calculation is so complex that it will take hours to complete. It will take all the resources of your machine. It's a heavy thing. And the only way of executing this is your computer. So you will be preparing things. You open the program that will run the calculation or simulation. You tune the input files or the parameters that are needed for the execution, and you just let it run. It's so heavy that it will take hours, maybe days. So the best that you can do is just leave it alone. Eventually, you can try to see if the computer still works for opening a web page, reading news, reading your emails or something like that. But still, that will consume a little bit of your resources. Probably it's so intensive that the machine will be paralyzed. You will not be able to do much else beyond just calculation. So that's all that you can do. That's the first scenario. Now, consider the next scenario is that now you have multiple computers. You have full 2, 3 computers on your room, and you can run stuff from them. So in that case, what you can do is, if those machines have SSH access, or you can just go directly to each machine, and the machine has its own monitor, keyboard, mouse. You can go execute one simulation here and another simulation there, another simulation in the next computer. And that way you can have multiple simulations. Eventually it's the same simulation, but with different temperature, different pressure, or the tube where some gases are expelling it is bigger, or they have some code or some different geometry, something like that. So different physical conditions will call you to run different simulations, and you have several computers. And probably you have more simulations than computers. So in that case, what you will be doing is some extra stuff, some extra task for you. It will be from time to time, you go check if the computer is still running the simulation, and if so, you leave it alone. You move to the next computer to check if that computer is still running the simulation. If it's not, if you have finished, you just prepare the next one and set it to run. That's another scenario. Many jobs, a few computers to run those jobs. So you will go in on each computer running the simulation. So you take charge of the execution, the monitoring, so checking if the computer have finished and it's ready to receive another job, and launching the jobs, the subsequent, continuously. And eventually some of those jobs could finish in the middle of the night. You are sleeping. There is nothing that can be done. Just when you wake up in the morning, you can check those jobs that are finished, you launch it, those new jobs. Now, going even further from those mental experiments, now consider that you are just part of a team. There are several users and there are several computers. And each user could eventually have many simulations to do because for some reason, some of them are preparing calculations for a poster, for a congress, and they just need to have that as soon as possible. So they will coordinate. They will say, okay, I will run this simulation. As soon as I finish, I tell you, so you run yours. So you will have to cross emails back and forth saying, okay, I'm running right now. It should be finishing in 3, 4, 12 hours. We will tell you, and the other will ask, okay, is ready now? Can I need it. I really need it. So you will be doing a human communication to try to be fair between the team for allocating the resources that are available. So many jobs, but still several users, so they will communicate. All those human tasks, the execution of jobs, the monitoring of the resources, checking which resources are available and which ones are ready for taking more execution. All those tasks can be the responsibility of a couple of software packages, sometimes a single software package. But we can distinguish a set of roles here. So one is the role of a resource manager, which is some software that it is connected to all the machines that are part of the cluster. They look like one single computer, but they are individual machines. And they will go and check if the machine is up, is operating, if it's running something, how high is the load on that machine, and it's keeping track of all the machines they are running. They periodically check the status of the machine, and they will communicate that to, let's say, a central server who is keeping track of that, and another machine, another software, sorry, which we call the scheduler, will take that information about the resources available, how is the status of the machine as a whole, the entire cluster, and assign jobs to those machines, trying to be fair for all the users that are requesting jobs. Try to not to put all the jobs to the first user that just arrived and they were lucky and they submit 100 jobs. Trying to be fair and trying always to have some resources available in case that someone who came with a modest set of jobs, maybe just one job, could still run that job in a reasonable amount of time. That is the role of an scheduler. Another role, for example, is like an accountant. For everything that happened, all the job, previous jobs, all this, to keeping track of all that. So saying, okay, this individual in the past have executed this number of jobs. This job took this amount of time. This other job asked for this number of CPU cores, this amount of memory, or a number of machines, 2, 3, 4 machines that were running for this job, keeping track of all that. Sometimes in some big clusters, those national labs, big infrastructure services, you receive a number of million hours, CPU hours, could be in terms of millions. So you are responsible for submitting jobs, and those jobs are counting from the hours that you're allowed to run. 2 million CPU hours. So if you want, you can just execute one job with one core, and they will consume a certain number of CPU hours. But if your job can be parallelized, you can get it in a shorter time, but using more CPU hours, core hours, let's say. So that is a role of an accountant. It's just keeping track of all that, checking how many hours someone is available, and as soon as those expire, this individual cannot submit jobs to the cluster because they don't have time available for them. So all that those roles, logging, monitoring, the resource management, and the schedule, all those. In our case, we have one software that is taking all that. The name of that software is Slurm. That is the name here that we have. In all our clusters, in Thorny Flat, Dolly Sots, the cluster, HIPAA compliant cluster, the CTSI cluster, all those three main HPC clusters, all of them use exactly the same software for managing the resources, for the work. We call it a workload manager. So we will see here, for example, in this picture, like a mental map of that, a little bit like the description that we have here. I told you. So you are a researcher here. So you are right here. You either connect to via terminal, so an SSH to the SSH WVU SSH gateway, from there to Thornyflat or Dolly Sots. So this is a terminal access, or via the web interface, which is something like this, where you can submit jobs. We will see that in a minute. You connect somehow to the cluster to a special node, which is called the login node. Behind that machine lies the entire cluster. The entire cluster has multiple machines with different configurations. Some machines could have more memory. Some other machines could have GPUs with them. Some other machines could have different numbers of CPU cores inside. So different machines, and those machines are organized somehow such that they all see the same home folder. So no matter on which machine on the cluster you are, you see your files. Your files are there. You are able to read and write into those location. And also the Scratch, but the big Scratch folder. So we separate the space for our users in two big pools, to put it that way. The home folder, which is limited to 10 gigabytes, and the Scratch folder, where the limit is around 20 terabytes. We have a big space there, so where you can put big data sets, a lot of data, but still, when you finish and you don't need the data anymore, it's expected from you to clean your space and keep it in a reasonable amount. And then you have all those cubes here are depicting different compute nodes. In the case of Thorny, we have more than 170 compute nodes, 170 machines. Most of them, they have 40 cores. So the total number of CPU cores on Thorny Flat is more than 6,000 CPU cores. A few machines like 11 or something, more than 10, but relatively a small number of those machines, they have GPUs with them. Most of them are P6000, RTX 6000, a few A100s, NVIDIA GPUs. And people launch jobs, and those jobs sit in queues, in a long job queue, or in multiple. We have actually multiple queues in the Slurm. Those queues are called partitions. They are like subsets of the cluster where jobs can be executed under certain circumstances. So amount of time, amount of memory, and number of CPUs, all that constitute a partition. So we will see that in a minute. And the scheduler, which is also Slurm, will see the list of jobs, check the users and the jobs, the specification of the job, and will launch those in the cluster, so into the cluster. So they will not necessarily is the first arrive, first serve. That could be unfair in the sense that someone just arrive with 1,000 jobs. If we follow a first arrive, first serve, the job will be completely held by that individual for days, weeks, eventually. So we don't follow that. We follow like a fair share, which is if someone will arrive with many jobs, it will execute some of them, but still, even if there are machines available, not all the jobs will be assigned. We will spare some machines for other users with modest amount of requirements or requests, so such that everybody is kind of happy. They run somehow, they run something. Eventually, if the cluster is really, really empty, this user with a lot of jobs will see many of them being executed at the same time, but not necessarily. And some of those jobs, as I mentioned, it will become active and will run on the different compute nodes. Some jobs could take just 4, 8 on CPU cores. So multiple jobs could run on the same machine, or a single job could run on multiple machines. If that job uses MPI or other kind of distributed parallel computing, they can take multiple machines, several machines with all the resources on those machines, and speed up the calculation. And that's perfectly fine. So that is what we describe it here in the picture. And we will be executing our first example of this. This is the idea. I will show you a very small script. It does nothing, just to show you that you can replace this script with whatever is the calculation that you plan to do. It could be a genomics, an alignment, or some genome that you need, or the simulation of gases in a combustion process, or a molecular simulation of a galactic simulation, or the collision of two black holes, whatever. You fill that with any kind of scientific simulation model or numerical calculation that you plan to do, or the training on a neural network, if that is you are doing something in deep learning. So that is the idea. That is what I will be presenting. I will show you the script, and I will show you how you write a submission script. I'm trying to be explicit as possible on how you execute that. So let's go here. So this is the cluster. I will be doing this very, very explicitly. So I will be going here, introduction to HPC. In here, I will go, see if I have it here. I need, oh no, this is very simple. So let's start with this. Let's start with the simplest example that I can execute here. And I will call it this and sleep script. I will show you what it does. All that I want to do is to put the machine to wait for, let's say, 30 seconds. Just that. It's very silly. All that it does is this. This command sleep, for example, if I execute it directly on this on the terminal, this is what it does. It does nothing. It just keeps waiting 5 seconds, finish. Replace that line, that is sleep 30, with whatever code, whatever Python script or R script or the simulation line. It doesn't matter. So I keep it as simple as possible. So this is what you are not supposed to do, to just execute this directly on the login node. So I'm using something that will take no resources, but still, this is not how you're supposed to run things on the cluster, because in that moment you will be just using the login node. Many people is using the login node. Many people relies on the login node being sufficiently idle, so with a very low little load on it, so it could process and receive commands and execute those commands quickly for all the users that are using the machine. So now what we'll be doing is converting this script that I just showed you into a submission script. How I do that? Well, I will be writing here a few lines. I will add in a few lines. All of those lines start with S batch something. And in this case, and I'm putting the options very, very explicitly, the long versions of those options, such that you know what we are doing. So let's see, let's replace the whole thing with here, right here. So I will be editing with my favorite editor. You can use Nano for this, and I will be writing this. I just copy here. I will be replacing all this. So this first line here is called a shebang. Usually it's like this. You are using bash. So what we have now is a file that serves two purposes. For one side is the execution that you want to do. In this case, a very silly wait through 2 minutes. So it's just that. So yeah, I will do a few extra things. It will just print on the screen or in a file, actually in a file, the name of the machine that execute your job. That's convenient. The date, it will just print the date in the usual format of date. And it will execute the command sleep, which means stop the terminal for 120 seconds, so a couple of minutes, and resume execution, and that's it. This is the first purpose of this file. The other purpose is a description of resources for the resource manager, for the workload manager, for the Slurm, to know what kind of resources you need for executing this. In this case, I'm saying, okay, I would like to execute this in the default partition of the system. And I will show you a little bit that. So the entire cluster is divided in partition, but it's not divided, it's segmented, if you like. Different segments could overlap. It's the same machine could belong to several partitions. Actually does. So there is one partition that contains most of the nodes, almost all the nodes that are not CPU, that they don't have GPUs with them. All those nodes, the large majority of them, of the nodes on the cluster, are part of the standby partition. This standby partition, they have a limit for the amount of time a single job can run. It's 4 hours, just 4 hours. It's a very convenient partition for most purposes. So to admit there are plenty of resources there to execute jobs. And if you are capable of launching that and get it something in 4 hours, that's the idea. Even if it's not possible to get it done in 4 hours, if you have the ability to get like a partial result in, let's say, 3 hours, 3.5, something like that, And you are able to do that. You are able to stop the execution, plan the execution to complete in 3 hours or 3.5. And you can resume the execution later and continue back and continue from the last position and continue the simulation. It's often convenient to use a standby compared to launching the job on the day queue or the week queue, because there are more resources available. So you get the end into execution faster. It all depends. Some people, they cannot do that. They don't have control on the amount of time, or you simply know that you are so close to need one day, you need like 20 hours or something, that it's not worth the extra overload for you to execute and re-execute. It depends, but the main thing here is that we have partitions. If you don't put this line, it will do exactly the same, because the standby is the default partition, so it's the partition that you will actually use. You can declare to Slurm a name for the job, which is handy when you are monitoring a minute. We will see that, monitoring the jobs, so you see which jobs are running. We can check the name and you know, okay, it's this one that I put. Some people encode in the name the kind of partition, the kind of molecule that you are dealing with, or the temperature and pressure, or the size of the simulation box, or the width of the tube for a combustion process. The different conditions for the simulation are encoded there, and you know what they mean, but only you know what they mean. That's the second line here. The third line is a declaration of the amount of time that you allow yourself to run this job. This is, I want 3 minutes. If 3 minutes is not enough, I prefer that job to be killed. Something is wrong with it. I don't allow this job to run for more than 3 minutes. If you don't use this line, if you suppress this line, it will take the default time from the partition, which is 4 hours. You will be allowed to run for up to 4 hours. This is a way of constraining in cases of that you are testing something that eventually hangs, or there are conditions under which the simulation explodes and takes longer and will not do anything with any physical meaning. So it's better to kill that. It's better to constrain the job so you don't waste your time running something that is going nowhere. That's the third line. On the fourth line, I am combining a couple of things. I'm combining a request for the number of nodes, which by default is 1. So you can also suppress this. And the number of tasks per node. We will discuss the difference in the Slurm between the task and the number of processors per task. So how you can declare the number of CPU cores that you want to use. There is not point to use more than 1 for this stupid execution. But just for demonstration purposes, I asked for 2 cores. So in the same, I want to execute a couple of tasks, and I need really 2 CPU cores. That's okay. So at this moment, what we have is a submission script. The two sections here are very clear. The execution itself and all those lines that, by the way, from the point of view of the shell, all those lines that start with S batch, those are considered comments. So they are ignored by batch. They are ignored by the shell. Slurm will read those. Slurm will process them. So what the shell does, what the shell is executing in the compute node that you receive for this purpose, are those lines, are these 4 lines here. So let's save this. So now you have it here. And let's execute this job. The way you execute a job with the Slurm for all our cluster is with the command. Oh, before executing that, let's digress for a minute into the partitions and the jobs and a few commands that you need to learn for this. So everything in this Slurm, in the workload manager, is basically executed with 5 commands, no more than that. And actually, you most of the time will execute just 4 commands. It's all that you need. And so I will express a little bit what you can do with each command. And I will be using the first one before executing this, which is the command sinfo. If you execute it sinfo, well, like this, you will see all the partitions in the cluster. You see here, just like this, are all the partitions here under the different states of those partitions. So it's a very verbose output what you get, because you get the same partition here multiple times, because some of the jobs, some of the compute nodes could be downed, some of them could be partially doing jobs, so they are done running jobs, but there are still some CPU cores available, so they are in a mixed state. So a few compute nodes could be entirely down. You cannot run them. The nodes belong to the partition, but they cannot take jobs at this moment. Some of them could be drained. That means that they could be executing something, but they are not taking more jobs, because in the future the machine will be down, and we are just letting the machine to complete, but not allowing new jobs to get into the machine. Or the machine could be on a mixed state. That means that from the 40 cores of one node, they are using 4, 8, 20, 30, but not the entire machine. So they are in a mixed state. Or they are fully allocated. So their machine are completely executing jobs, and those jobs are meant to take the entire 40 cores on them. So all those, and they express those in a very compact way. So all the machines from the TARX 300 to the 304, and all the machines from the 400, 401, 402, 403 are in this list. So it's a very compact way of announcing the list of machines that are allocated. And the same is true for all the different partitions of the system. So the small day, the small week, all those that start with com are community partitions. That means that the machines associated to that are for everybody. So those machines were purchased with the grant that we got from usually NSF, and everybody who has an account with us can run jobs on those machines. And so there are a few here for extra large memory. So the first part is saying, okay, this is a community partition. The second section here is the amount of memory of the machine. So a small memory means that that machine has 96 gigabytes of RAM. You can take out 6 to 8 gigabytes of RAM because they are used by caching the distributed file system. So you cannot actually see or work with the 96. You should assume are something like 88 gigabytes of RAM, roughly speaking. So that is the definition of a small memory. Medium memory is double that, so 180. An extra large is 768, so 760 gigabytes of RAM. And there are some kinds of simulations, some kind of processes. For example, in bioinformatics, sometimes you really need to put the whole data in RAM. So we don't have many. So they are in high demand, but they serve a very narrow set of use cases. Extra large memory, a few machines with GPUs, those are here. The interactive partition and the weak partition. We have one which is kind of some special machines that they only have 20 cores for running for a day. And so, and the third part, the third section here in the name of the partition is the amount of time that you allow to run on that partition. So the small day is allowed to run for up to 1 day, 24 hours, and week up to 7 days. And the other partitions here that you see here are partitions from professors, from faculty members who have purchased nodes that are attached to the cluster. They receive their own partition. They can run on those machines for as long as they want. So they don't have limits. So you see that all those partitions, that limit is infinite. But if the machine associated to those partitions is not in use by them, they still belong to the standby queue, the standby partition, so they can receive jobs that they will be running for up to 4 hours. And if the faculty or students belonging to the group request a job after those 4 hours, the priority will return to the owner partition, and they could run on their own resources for as long as they want. So that is the idea of that. If you don't want to see such long description, there is like a summary version of that with -S, and in this case here encoded in this column here, in this column, you will see the number of allocated, idle, in other state they drain, and the total number of compute nodes on that partition. So you see 173 compute nodes are associated to the standby partition. From those, 53 are executing jobs at this point, and everything else for the other partition. So that is the first command, sinfo. There are other ways of looking into those things, like at the script. I think it's like this. A list for all the nodes and the condition of the nodes. Usually people don't execute those. Keep in mind this command. This command is useful, especially if you just get access to a new cluster. The first thing that you want to do is to check which are the partitions on that cluster. So this way you see that really quickly. That's the first thing. Now this is a good time for showing you how I submit jobs. I return from my discretion here on the partition information, and let's go back to the submission script that I have here. So I will be submitting this job that contains these specifications for the job, and this is what I would like to run. The command for that is sbatch. So this is the second command that we will be running, sbatch. When you execute this, you receive a number. This number is what is called the job ID. It's a unique number that you receive when you execute a job. And everything that you want to do, if you know the number, you can check how the job is doing. And that lead us to the third command that we want to learn. And it's SQ. If you execute just SQ, you will see all the jobs on the cluster. There are many. And the state of the job, you see here encoded that, if it's pending or if it's running, all that. But we're just, most of the time, we're just concentrating on our jobs, not everyone's, other people's jobs. So there is a --me, which means my jobs, just my jobs. So this is something that you want to use. You will see here the job ID, the state of the job, so it's running, on which node this job is running, and the amount of time that has been in execution, so 25 seconds. And it will run for a couple of minutes, so it's halfway in the execution. And the partition, this name of the job that I told you, I put in the second line of the description, my username and the state. So this job will still be in this list as long as it is in the queue. If it's pending for execution or if it's in execution. As soon as this finish, or a few minutes after it finish, it will disappear from the list, from the queue, and you will not be able to see it with this command. So we will be using another command for that. Allow me to see that. It will take like in 10 seconds. I would like to see. Now it reached the 2 minutes and it disappears. Now it's no longer here. So this is important because in other resource managers, they could still show you jobs that have finished long time ago. That is not the case with Slurm. As soon as the job finishes, sometimes a few seconds after that, it depends on the configuration, it will disappear. It will not be here. The job, something happened with the job. The job finished, the job failed, but it's there. So, but we still know that that the job existed, was executed. So we can use here the job ID to check on the job. And this leads us to this. It was sinfo, sbatch, sq, the third. So they will be the number 4. Show job. And for a while, this will show you some information about the job. The 4 command, scontrol. Scontrol does many other things, but from the point of view of the user, this is what you usually want to do with it, checking the state of a job. So you will see a lot of things here. When it was submitted, when it started running, so the submission time here, when this job became eligible for execution, and the start time, the end time. So that is one time-related section of this. There are a few things here, so like the partition here. What is the partition? Partition is here. And the specification of number of nodes, number of CPUs, number of tasks. We will see that in a minute, the difference between how we can request tasks or CPUs in different ways. If you request GPUs, they will be mentioned there. And where in your file system will be located the output and error of the job. So whatever that is meant to be shown on the script on the screen, if you execute this directly, it will go to a file, and it's this file. So let's check that file. Let's learn 1.7, this one. This is the content of the file. The cat will do the same. Remember that on my submission script, I ask, okay, write this. This script is running. Okay. This is the name of the machine. This is what happens when you execute hostname. But this is not executing the login node. It's executing another machine. And this is the name of the machine. And this is the date when this was executed. And after that, it was just on sleep for 2 minutes. And that's it. Okay. And so this is the for command. When the job can be executed for a long time ago, you want to see something that you execute a week ago, a couple of weeks ago, will no longer be shown here with the command S control. Even a few minutes, a few seconds after that, the job completely disappears from the view of S control. So the only way to see information about that job is in the accounting command with the S account under J and O here. So it will show you the condition of the job when you finish, if it's complete, if it's something fails, if something went wrong, it will appear here as fail. And if you want to see a very, very descriptive, there are two options. I don't like this much, or I show you in any case. To see that it's like a long, very long multi-column kind of thing. It's so long that the columns are condensed. It's not easy to read anything from this, because here you see the names of the columns, but you need to figure it out what they match with the value. What I usually use is instead this. You give me all the information, the entire information, in a JSON form. So it's something that is, I consider more manageable. I can go back and see the number of CPUs, the machine, what happened, what are the logs, all in a very granular detail, all the information. This is one way. Or there is another option to check this, and you can see here in the manual. Okay. That you can put here and the argument -O and declare a format for the kind of fields that you want to see, that you're interested to watch. And those are the fields that you want to see. So you can put all that. Let me see if there is one example here. I think that there are a few examples here at the end. No. Yeah, a few examples here. So imagine this, let's say, just to give you an example. You can see certain fields just to not cross the limits of your terminal. Just select a few things that you want to see. So let's recapitulate, because this is all that you need, plus one command, and that's it. That's how you cancel jobs, which is something that, let's imagine that I will re-execute this. And I'm not happy with that. I realize that I should have been done this differently. I want to cancel this job. So the command to cancel the job is cancel, and that's it. So if you execute here, it will say nothing. The job is no longer there. And if you execute s control show job, it will show as cancel. So let's recapitulate, because this is all that you need to know. And after I will show a more complex executions, but this is the most important thing to learn for effectively using the cluster. It's just those commands. First command is info, usually like this, to show the partitions, and eventually gather information on which partition is under heavy load. So I shall try to go into a different one, especially if I have some flexibility. I know that it will take 1 day, but I could be using the small or medium because I'm really close to that size of memory. So I could try. I need medium, but I can test my chances that my job could run with a small memory partition. So you check which of those are in better shape, and you submit there. Though those are things that you start, tricks that you start learning over time. So you do this and you check, okay, maybe it's this or this one. Okay, this one looks quite busy right now. So maybe the medium memory give me a chance here. So because no jobs are allocated there, all the 5 nodes are idle. So if I execute it there, I will go and execute immediately on that machine. And this one, or for example, this one, that sometimes people use this one because they only have 20 cores per node. But some people is happy with that. 20 cores is still a lot of processing power. So if other queues are under heavy load, people can decide, okay, maybe let's try my chance. Once you submit to a certain partition, you are attached to that. So you decide in advance. So that's the first command. The second command that we saw is the sbatch for submitting the job. I show you the like the sixth command, the last command to cancel the job, which is this one. But let's consider this is just a very small command. So that I don't count on this. So it's sinfo, sbatch, sq for looking into the all the jobs, the partitions assigned to them, and if they are running or not. Or better, I use this one all the time just to see, to look into my jobs. So this is third command, is control, and I show you that to look into the description of a job, or command fifth is act to look into a job that has finished probably long ago. So this is an accounting command. Seldom used, but still something that you should. You do basically everything with those commands. That's all that you need. So now let's go into some details, descriptions, things. Okay, what happens? This is something that I'm doing here for the wall time exercise. So what happens? This is something that I present. So I will be exaggerating here a little bit. So imagine that I'm asking 10 minutes, but still I will keep this sbatch as it is. with a limit of 3 minutes. That's a small exercise that I will be doing. And I will submit that. Okay. And in the meantime, there will be, well, probably it's right now in execution, it's running 3 seconds. So in the meantime, I will explain a little bit some other things. So here, I am declaring 3 minutes for execution. The format for that is hours, minutes, and seconds. And you can check that the amount of time that the job has been running with SQ. That's one thing. So in this case, well, it was not, well, this is the original. So I executed 2 minutes, but I allowed the job to run for 3 minutes. It's okay. So now imagine that I request a longer amount of time. So you will see something like this. The job will be canceled. So it's Slurm will kill the job back on the compute node that is executing that. As soon as it crosses the 3 minutes wall time. Let me see if we actually, oh, if that is the case right now. Let me go here. So it's, wow, it still has a few seconds. Let's describe in here a little bit. And this is for our cluster. Most nodes are like this. So we have 40 cores, but you don't need to ask for 40 cores. In fact, it only makes sense to ask for many cores if your code is capable of some parallelization. In particular, is capable of multi-core parallelization. It's not trivial. It's not granted. Just for getting more cores, your job will not finish faster. It's a little bit like the sleep code. It doesn't matter if you ask for 40 cores. If you are executing the command sleep for 120 seconds, it will take 120 seconds. Period. No parallelization is happening here. In some codes, for some codes, in basically all domains of science, people have developed algorithms that take advantage of the multiple cores and divide and conquer. They all divide and conquer. You try to do some execution on this core, another execution on this core, and after gather the partial results, do something else at the end. That is something that happens. I know, for example, if you say in bioinformatics that I know, BLAST, for example, is a code where you can, there is a command line there that is -T, when you can select the number of threads. You can parallelize the execution of BLAST. There are some other codes, GAT cake, I think is the name of the code. It's a Java code, but still, you can declare how many parallel threads you can run. So in bioinformatics, there are codes. Not all of them, but there are a few very important codes that can take advantage of parallelization. In physics, almost all codes in physics are parallelized somehow. If you are talking about molecular dynamics or electronic structure codes, all of them, yeah, all that I know, include some sort of parallelization, including multi-core parallelization, simulating galaxies, simulating collisions of astrophysical heavy objects like neutron stars, black holes, all that is so heavy, it's so computationally heavy, those kind of simulation. There is no point of not adding parallelization somehow. So parallelization is a precondition to have a scientific code today. And that is true also in engineering, for computational fluid dynamics, for finite elements, for mechanical simulations, models, all that is parallelized. And deep learning, vision, computer vision, all those, well, those are usually deep learning, which is parallelized in another way using GPUs. They And so basically in all areas of science or data mining or data science, or in all areas, parallelization is there. You try to parallelize, otherwise it will take ages for that. And you can decide different number of cores, not because you are for the all 40, you get the best execution. So you try to be moderate, or try to be reasonable with this. And there are several ways of doing this. You can request just 4 cores, 8 cores. Most of our machine, they have 40, but it's okay to your request just a portion of that. It makes sense for you because it allow you to run more jobs. The number of jobs, there are limits in the partitions for the number of CPU cores that someone can take. So if you just maximize that and you request 40 all the time, you probably just get 10 jobs running. But if you request just 20 or 10, you can get 20 or 30 jobs running simultaneously. So it's also in your best interest to moderate the number of cores, because otherwise you will be penalizing yourself and not gaining anything out of that. Some other codes use another kind of parallelization. This is more rare, but still, in scientific computing, in high performance computing, this is also heavily used, commonly used, which is distributed parallel computing. It means that multiple machines, several machines, can work together and communicate data during the execution, such that all of them can solve the same problem. They are working on the same problem, probably in portions of the geometry, different portions of the geometry, and they are communicating information about the boundaries. But if you imagine that you are making a simulation of gases flowing on a tube or something. So you can divide the tube in pieces. All that you have to do is allowing one machine one core to do a portion of the simulation and communicate on the boundary what is happening with those gases, pressure, temperature, all that, such that the simulation in the next time step is consistent for the next section of the tube. So that sort of parallelization, distributed parallelization, allow you to ask for multiple machines. So you can request more nodes. And in the option -- nodes, you can request 2 nodes, 4 nodes, 16 nodes. The machine, the cluster has 170. You have little chances to request 100 or more compute nodes. But if for some reason you really need to do an extremely large simulation for a publication, which is typically what happens, you do small examples, and after you prove your case for the paper with a big execution. So at that moment, you probably need 10 machines, 20 machines, and we allow you to run that job on the cluster. And you can request a certain number of machines or some number of cores to be assigned to what is called a task. In the case of MPI, is the rank of execution. So one process that is responsible for a portion of the job. So that is declared in the task per node. Let's go back here because that for sure have disappeared from here. It's no longer here. And the job was this. So what I will be doing here is looking at the message that I get in this learn. No, just one here. And you will see here, the job was canceled. It's not me who canceled the job. It was actually killed bias learn when it reaches the 3 minutes wall time. It was allowed to run for 3 minutes, but the sleep was for 10, was allowed to run for 3 minutes. But when I put the sleep, I asked for 10 minutes. So it will kill the job. No way. Okay, so let's see here. And there are a few other things. There are actually many other things that are beyond what I have time to demonstrate here. And I really want to demonstrate the job arrays. And I have like 15 minutes for that. And let's say if you want, you can go here and see all the options for this batch. So there are many things. Many things that you can do with this, that you can put in the lines here. Example nodes, here, nodes, CPUs, CPU. So you see all those options that you saw here, CPUs per, oh, in this case, I captured just one, CPUs per GPU. I was interested in looking into this. Dash C or CPUs per task. This is one way for asking a number of CPUs that you want to run, for example, in multi-core execution, when they call in BLAST, for example, in those codes that allow you to ask for multiple cores assigned to one process. So that is what you will use. But I would like to go into something else here. Other ways for submitting jobs. One is here, for example. There are ways to looking into the jobs here. Let me see. Okay, so here, or using Open on Demand, you can see all the jobs. So all the jobs, you can make the whole list here. Disappear. So you can get exactly the same that you get from SQ, but in this case, under nice graphic user interface, you can see all the details of the jobs. So for some people can find this convenient. That's one thing. And also you can submit jobs here. So I will try to skip this. I will skip this. If someone is interested in that later after the break, I can demonstrate that. But there are ways to submit jobs just from the graphic user interface. If you don't want to go into all the submission, and it's kind of ugly. I don't know what's going on here. I never use it, so I didn't check what I was not aware of this ugly thing. There are ways to prepare jobs and submit jobs from the graphic interface. But I want to go into something that is probably far more interesting, far more important for the users, which are, okay, these partitions, okay, the variables that you can use inside the job. So they are defined. So when you execute the job, and I actually can show that. Let me see, show that. Forget about this. I will show you this, which is, I will make it very small here, but I would like to see all the variables that are assigned by Slurm when it executes a job. So I will show you. There's a long list of variables that you will see in a minute. And this is just a small portion of those. Those that are, I found useful, commonly used, and variables that you can use inside. How you cancel a job, all the batch, and how you submit interactive jobs. But I really want to devote this time. Later I will show the interactive jobs. Are the jobs arrays. because this is really useful. Many people want to do simulations, many simulations. It's the same simulation, but you want to test under 200 Kelvin, 300 Kelvin, 400 Kelvin, 500, or even more granularly from 10, from jumps of 10 Kelvin each time, different pressures, different densities, with a certain configuration of galaxies, more dense, less dense, different sizes for the black holes. Well, whatever you want to simulate. You probably want many simulations. They're exactly the same except for one parameter. So what I'm doing here is demonstrating how you do that. Instead of writing one by one, let's say 10, 20 submission script, which is very prone to error. At some point you will make a mistake and one of those files will get different input, will be slightly different. It will damage your simulation, or at least a portion of those. There is a better way of doing that, and it's using job arrays. A job array is a way of effectively launching many jobs from one submission script. Very useful. Many people use this on the cluster, so don't feel bad if you launch 20, 50 jobs. The cluster will take those 50 jobs. Please try not to submit 1,000, 10,000 jobs. It will make the cluster, or it will put some difficulties on the cluster. More likely, most of those jobs will be put in a hold, so they will not be running or in queue, and they will be slowly getting integrated into the queue for execution. They will be allowed to execute. But this is the idea. I have a script now that is meant to compute a certain number of the Fibonacci series, something very simple, everyone understands the Fibonacci sequence. The important thing here is that I would like to use an array here of elements that goes from 1 to 10. That means that there is all the jobs will be exactly the same, except for the presence of one variable, just one variable. That is this variable here, is this variable here, that is different. And I will use in my script the content of that variable to decide different executions. In that case, the number of elements in the Fibonacci sequence that I would like to get. So this is the script that I'm doing here. And let me see, I will be copying this. And I will be executing this. So I will be, well, I already have it probably. Okay, this is, I did it last time. So I will be deleting this, and you see here. It's exactly the same example. I already copied it. So everything you know about this. So this is exactly as my sleep submission. But now I have an extra option here. It's called SBatch array 1 to 10. I will be using this, and with a mathematical expression, I don't need to do it. I did it this way, but it's not mandatory to do so. I will be using this variable, or the content of that variable, to define how many elements in the sequence I want. And I will be taking the number of elements based on that information. You can do exactly the same, taking an array, and based on that number, going, for example, to a different folder and do and the alignment of a different sample that you got. Imagine that you got 10 samples of an animal or plant or whatever, and you want to do the alignments. So you have 10 samples, you have 20 samples. So you can use the array to go to each folder and do exactly the same, but do just one submission script. If something fails, the next time you can resubmit the job and change just the array. There are ways to select just, I want just this element. Just declare like a list of cases that you want to re-execute, for example. So this is what I'm doing. I will be submitting this job. And I will get this. So if I execute this, I will see all the jobs here. They are in a pending state. So they are waiting. Probably now they are running. When they start running, those that are running, they start being listed here. They have the same job ID with underscore and the number from the array. So one submission script allow me to run 10 jobs here from 1 to 10. Let me see if they're still running. As soon as they finish, probably some of them are finished now. Let's learn, let's say the one. You will see. So I'm taking number 1 and number 2, and I'm building the 10 elements of the sequence using those 2 numbers. So 1 plus 2, 3, and after 2, 3, 5, 3, 5, 8, and so on and so on. And that's what I'm doing in this case. In other cases, imagine, for example, the number 8 that probably has finished. In this case, I'm starting from the 8 and 9. So I'm starting with 2 contiguous numbers, and 8 and 9, 17, and from there. So that is like a Fibonacci sequence, but with a different seed. Put it this way. I start from a different couple of numbers. I am building the sequence starting from there. So that is something that demonstrates how with a single submission script, you can launch tens, probably even hundreds of jobs. And you know that all of them has the same instructions. They're doing exactly the same, except for one variable that we define which folder or for which file are you planning to do the execution. So that here is the description of that. And let me see. Yeah. And now that I have 5 minutes, I can show you a little bit about the interactive execution. When you are submitting here on Thornyflat, here with the Python or R, here, let's say, imagine R, for example. When you launch R here, you are actually launching an interactive job. This is one way of, let's say, feeling this. This is an interactive job. It will be listed in my list here of interactive jobs. And I go here, my jobs. Is listed here as an interactive job. There are other ways of launching interactive jobs. So one of them is with the command srun. Srun, and this is one way. You see, for example, like this. Imagine that you want to execute something here. In this case, you can declare the partition, the amount of time that you request, the number of minutes. In this case, is 40 minutes, 0 seconds. Number of cores that I will be using, that I'm requesting, and I would like to get an dispatch. So notice that the compute node changes from this one to this one. This is one way of executing interactive jobs. At this point, I don't have what. At this point, you can, for example, load, module load, length, GCC 12, and length, CPython 11, Oh, model purge. Now I get Python and I can start executing IPython and playing with that. I will be using, I think, 4 cores. So I have 4 cores to run with this. If you are doing a neural network training and you want to have control on that, this is one way of doing it. If you prefer doing it with from the command line interface. Otherwise, if you prefer to do it here on the graphic user interface with RStudio, with Jupyter Notebook, those are interactive jobs. We have a couple of queues for that. So I will be killing this. I will be leaving here. So the jobs have finished. So there are just a few partitions, apart from the partitions from as info, that are allowed to run interactive jobs. In particular, a standby, you can do that. There is this interactive community GPU interactive is this, and all the jobs here for all the partitions from faculty who purchase nodes with us, they are allowed to execute interactive jobs as well as non-interactive. So with this is, I think, what is important to know about submission script. I will be pausing for 15 minutes. And when I will return, we will devote the second hour and 15 minutes to TMAX. And if you have questions, I will be open to answer those questions, to entertain those questions as soon as we return for the session, okay? So I will be pausing here 15 minutes as soon as we return. TMUX, the terminal multiplex, which is another important thing to use when you're dealing with HPC clusters and you execute and you use them very often. And sometimes you have several computers, you have your laptop, you have that home, so you can move between your office, home, and you want to continue working with how to reconnect everything there. So TMUX is really, really useful. It saves you a lot of time. So I would like to demonstrate many things around that. So 50 minutes, we will be returned. Okay. Okay. Let's try to devote a little bit more time to this section, which is very important when you use when you have access to multiple clusters, like is in the case in WVU, we have two main clusters. So some people end up using both, or you execute, you interact with the cluster a lot. So you want to keep, in principle, multiple terminals, and doing that and keeping your workflow reasonable across multiple machines. The best way of doing that is using a terminal multiplexer. This is what we will be describing here. This is like, imagine, again, another mental experiment. Imagine that you are working on 2 or 3 projects, on each of them requiring some simulations, some sort, on the cluster. Eventually, let's say, 2 of those projects are CPU based, so you use Thorny-Flat, but there is one extra project that uses molecular dynamics, or you are using deep learning, and for that you are using Dolly-Salts. On each project, you are checking your jobs. If they are finished, you are probably, after they finish, you run some post-processing tools, usually Python scripts, or RStudio scripts that will take the data generated by the simulations and collect the critical pieces of information that allow you to create plots, some scatters plots that will go on the paper, some other lines that will go to a different section of the paper, and that for a couple of projects here, a couple of projects there. So you will like to have terminal access to both clusters, and on this cluster you will ideally like to keep terminals for this project, and some of them you are monitoring jobs, and some other you are executing post-processing tools. So all those things lead you to think that it could be convenient to have multiple terminals. If you sit on your office, you have a desktop computer in front of you, that's probably not a big deal. You just open multiple terminals on your computer, on those terminals. Here you connect to Dolly, here you connect to Thorny, here you are checking the jobs, and here you are running the post-processing. And you finish, you go home, but everything will be on the desktop computer that you keep on your room, and that's it. But what if you are working with a laptop, notebook, machine? At that moment, as soon as you close the machine, you go home, or you go somewhere else, all those terminals will die. They will disconnect from Thorny, and the next time you need to do the whole thing all over again. So you connect to the GP and get away from there, jump into the cluster, and from there going into the directory where you are doing the post-processing or checking the jobs, all that. So you have to do that over and over again. The solution for that is creating like a virtual terminal, actually multiple terminals that sit on the remote machine, in this case, Thorny-Flat, or Dolly. And from there, those virtual terminals survive, or the state is kept such as that the next time that you connect to the machine, you can recover all those terminals, all the locations, or everything that is happening there. is recovered with a simple command. That is the purpose of a terminal multiplex. The ability to create multiple terminals and eventually dividing those terminals. We will see that in a minute. And keep the state of that, not rely on your computer, which could eventually be shut down, will be disconnected from the network, from internet. But consider that into the cluster and you recover from there. Let's explore this with examples. So see, I'm actually using one right now, so I will be leaving that. So the command for that is tmux, terminal multiplex. You can have multiple, let's start before entering into the taxonomy of all this, which is the critical part of it. Allow me to show you how you create a session. So you connect to the cluster, so you connect to the SSH gateway, which is controlled by ITS WVU. From there, you jump into the cluster. In this case, I'm using Thorny. And from here, I will be creating a session. To create a new session is just executing the command tmux. And you get an entire new session. Everything that you do here is preserved in case that you close this terminal and can close the computer. Everything is, the state of the system is on Thorny. So as soon as Thorny is not rebooted, for some reason, some power outage or something that forces us to reboot Thorny, if this doesn't happen, this session will stay indefinitely on the system, and you can recover that. Better than that, on this session, you can create two elements, two extra terminals in different ways. One is adding more windows here. So, and this is the terminology in tmux. So I'm trying to keep the concepts using the terminology of tmux. But before that, all the commands here for tmux, they use like a prefix or key combination that allow tmux to realize that those are tmux commands and not something else. By default, that key combination is Control B. Some people, depending on the kind of software that they use or other packages, they sometimes can rename it to Control A. But I will be using the default, it's Control B something. Let's go here and review this. Okay, so if I detach, for example, if I leave this throw, I imagine that I close the computer. I can retouch to the session with Control A. There you go, tmux space A. I'm attaching. In my case, I think I have now several of those. There is a tmux list. The shell. Tmux. What is that? Yes. I will see. I have several sessions in my case, but I will attach into one. It doesn't matter. Now, here. Oh yeah, and there is also another ways to create new sessions. So the first concept is the concept of session. I have multiple sessions in this system. And after that, I can create two things. or two terminals in different ways via windows or panes. Everything is with Control B. So I will be demonstrating how I create new windows here. Control B, C. The effect is you see on the bottom of the screen. Let's see if I can make it smaller here so it's easier for me to see. So on the bottom, on the green long line on the bottom, you see a number 0, number 1, and after bash. So 0, bash, 1, bash. Those are windows, and I can create multiple windows. Control B, C will create an extra window. This is the first way of creating terminals. Those are independent terminals. Right now, they start the same, but they could be doing different things. So I could be jumping. Okay, I jump into between windows with Control B and the number on the bottom. Control B 0, Control B 1, Control B 2. Those for the first 9, for the first 10 actually, from 0 to 9, I can use the number to jump between the different windows that I'm creating there. So I am pressing Control B 0 to go to the first one. And here I will be executing, for example, the command tab. This is in the window number 0. On window number 1, on window number 1, I can jump into that window with Control B 1. It's a different terminal. I could be listing my files there. Let's see. And now I have Control B number 2. And here I am executing, for example, SQ and looking into the jobs being executed in the cluster. So with this, I can go Control B 0, and here I'm running top. Control B 1, and here I'm listing my files. And eventually I would like to go into a different folder. So this is, I have here the folder. I'm looking into something here. And Control B 2, and I will be here monitoring jobs. This is the first way of creating terminals, virtual terminals that are attached to the same tmux session. Now, you can also divide a window into multiple panes, and those panes are also terminals, and you can do things with them. So for example, here, I can divide this window here, or I can create a new window, for example, here. And I can divide this window horizontally, or better, vertical, because I want to do something. And in this case, it's Control B percentage. In my case, it doesn't look so nice. I don't know. Usually it has like a green line. I don't know what is. Let me see if I should close it. It's static, but somehow the terminal in this virtual terminal that I open with Thorny is somehow interfering. Well, it's statically with how those panes are shown. So what I will be doing instead is I will be using my own terminal here. And so I will be changing my sharing into a sharing for the entire screen. Let's see if that's better this way. And this way, let me see if I can go SSH. Okay. And I will be making it a little bit bigger. little bit big. I don't need it that big, but that's it. Okay. And now I am throwing flat, and I will be attached. Okay. Let's keep this on the background, and let's keep this. Okay. So now I can create new terminals, new windows here. I can split them. This is what I was saying, that normally it will make a vertical line, color it properly, such that I could identify where it finish one pane compared with another. So that is with Control B percentage, I am making another panel in a separate column. So I am adding extra columns to this. But there are also ways to create new panes horizontally. Control B, Control B. What is this? Let me see. Okay. Well, then another way of doing this is reorganizing this. This is what I used to do. So here I have three panes on this window. So I am running on one session. I have actually multiple sessions, and I can change between those sessions. So you can have multiple sessions. On each session, you can have multiple windows, like number 0, where I was, let's say top, number 1, Control B 1, I killed 1, 2, and 3. Well, I renamed 1 by mistake. And in number 2, I think I have this divided by panes. On those panes, I can execute more commands or opening things. For example, there is one for showing a clock, like an ASCII clock, that sometimes could be handy to have. It depends. And here you start cycling your focus between the different panes with Control B O, Control B O, and I will be jumping here. Control B O, and I will be on the bottom left corner. So SQ, for example, like this, if I'm monitoring my jobs, and I can reorder the layout of those panes with Control B space. That's what I do most of the time. So there are multiple layouts depending on the number of panes that you have. They executing multiple times Control B space will change the layout for what you think is more convenient for you at that moment. So sometimes it's good to have multiple terminals and doing something on the one and checking something else on the other. You can rename the panes. All that I am probably jumping here and there in the different things that you can do here in the description. I am just picking things that I would like to show you. So you can rename the windows. So in this window, for example, in the window being this number 3, I can put a name for that. So right now it's here, it's called top, but I would like to, let's rename it anyway. Control B, comma, and allow you to rename this. So you can put the name, for example, you are working on a project. So for you to be aware of which is the purpose of that window, with that terminal there. You rename the window, and you know it's project this. Let's say here that on the number 1, here I will be monitoring with the Slurm, monitoring jobs. So I will call it, let's say, slurm. I will put a name to those. And here, let's say number 2, I will say time, control B, comma, and I will be I will be doing some monitoring or time management thing with the different files for the project. So this is another command, control B, comma, and allow you to rename the different windows. Now, there is one command for looking into the whole spectrum of windows and the panes and all that. It's control B, W. So here you see that I have one session here. I have 3 sessions. This session, this one session that I was creating before here is this one. Oh no, this is something that I was working. So this is my usual one that I was working for some project. So this is one here. This session has 4 windows at this point. There is this session here where I rename the windows, slurm, time, and top. And there is another session here that was the session that I created before here on this virtual terminal in Open On Demand. So Control B W allow me to see the different terminals, different sessions, different windows on those sessions, and different panes on those sessions. They will tell me how many panes are on each. Allow me to create some. So Control B, let's say, I usually create 4. I create 4 and I use Control B space to reorder those probably like this. So I have 4 times 4, 2 times 2, like in a grid. Sometimes I reshape those depending on what I'm doing, and reshape those different panes. And now, if you go here, Control B, escape, Control B W, Control B W. On the bottom of the screen, or the bottom half of the screen, you will see like a representation, like a cartoonish version of the corresponding window that is shown for that corresponding session. So those sessions here, that is the session that is currently attached. Now I am attaching this one here, and I'm looking into this session here. This will show me also which is the session that I'm attaching to, the number of windows, the number of panes. Here, when I have, for example, this pane here, this pane here. For example, I want to Control O. I will be cycling between the different panes. And I would like to take all my screen to working on this because I'm editing a file. So let's say Word hands-on, introduction HPC, and I would like to go into this one. And I would like to edit this file. So my space is too short, it's a long code. I could execute Control B Z and remove the other panes. They will disappear. Here on the bottom, you will be seeing a star and a Z. And that Z means that there are more panes that are not visible at this point. Now I can go editing the file, and if I want to recover, zooming out from those panes, and press Control B Z, and I recover those panes. So that's a way for zooming in, zooming out from the panes. Let me see if I am missing more stuff from here. So you attach with Tmux you go into the different windows with Control B and the number, or you can do the same with Control B N for the next window. Control B, next, Control B N, Control B N. It will be start cycling, which is the only way. For example, if I create several of those, now I have 7 windows here. And this one, I'm doing this. On this one, well, different things. So Control BN, Control BN, Control BN allow me to start switching between the different. If I close this window right now and I reconnect to the cluster and reattach, everything is preserved. If I am editing a file, I will continue editing the file. I don't have to reopen. I don't have to change the directory. I don't have to do anything there. So everything is, then the state of the system, the state of those terminals are all that is preserved. What else? If you create more than 10, so from 0 to 9, you create more, only the first you can direct those with the numbers. Beyond that, you have to use Control B and Control B. To go backwards, instead of, let's say, I am number 5 here, there is Control BP for going to the previous window. So you navigate through the windows with Control BN, Control BP, or with the number Control B and the corresponding number for the window that I would like to use. So that is here. Control BP, Control BN. You can kill a window with Control B ampersand here. So here, you want to suppress this one. It will say, okay, kill this window. Will say yes, and it will make a hole in the number. It will not renumber those. It will say window number 0, number 1, 2, 3, 5, 6, 7. So those are this is what happens when you kill one window. And see, okay, for horizontal, let's see, Control B. Oh yes, okay. This is how you create horizontal new panes, and Control B percentage for vertical new panes. And what else? Oh, okay. This is good. Imagine, let me see. I will be cycling here, and I will be executing this command, dmesh, which shows kernel messages, or it's a long list of stuff. And I notice, okay, there are things that I would like to check. Some problem is happening. And okay, first, I am getting half of the space, and I will really want to look into this file. So I will zoom in to this pane. And this file is too big. So I'm not able to see all that. So I would like to scroll in that file. So the command for moving into copy mode is Control B and opening the square bracket. Okay, opening the square bracket. And you will see on the top that it shows in the square brackets the lines that are currently there. And from that, you can use the mouse. There are the arrow keys, or I could use my trackpad on this Mac to go and read the file and checking what is going on with this. So this is one way of doing things. You can also here use this for copying and pasting. Sometimes it's just easier on a Mac, on a Windows machine, or whatever. You just copy and paste. So the internal copy and paste, the operating system on your client side, it probably do the same thing. So, but if you want to know, there are ways for doing this with the spacebar. It works very similar to Emacs. So with spacebar, you start the selection, you make the selection, and after you copy that and paste that somewhere else. Okay, now there are some other things that you can do with this, like changing the behavior of that. Some people is really aficionated, let's say, really passionate about demugs. I am just picking one example where you can edit this demugs file, so the configuration file. If you edit this file, you can change the coloring, the information that is shown on the bottom. I don't remember all the things that you do with this, but let me try, because I really showed this long time ago. So this is the file is the doctimax.conf. So I will be doing this here. And so first, let me see. I will be leaving this. I will be detaching, and I will be Emacs. Well, I have now one option there, but let's see. Let's remove that. And so I am copying and pasting this configuration file, just to show you that you can change a lot of this. So the different lines, so well, that's beyond, but I can show you here. Emacs 8. No, let's see if I can. Probably need to create a new. Well, it's not doing much. It's not working. Okay, maybe something had changed in Tmax and the file is no longer working like this. Anyway, what else is important here? Let me see. Oh, okay. Of course, I'm working on multiple clusters. So what I'm doing when I will be leaving this Tmux, attaching this. Okay. So what I'm doing usually is I have multiple sessions. So here, let's say on this session, it's dedicated only for Thorny. And I could have, let's say, this session here dedicated exclusively for Dolly. So that way I don't overlap when I'm doing with one cluster compared with I'm doing with another cluster. So I will be control V0, I will be killing this. Even if the session here is running on Thorny, which is, I consider a more stable login node in general. I could use that one to go to create new terminals on Dolly and rename those. Will be. So I know that I'm working on Dolly sometimes, and in the next terminals, I working as a root, or I have multiple usernames or multiple users on the machines for administration purposes. So I always try to put tags on the bottom for them. So that way, when I'm working here on my list of sessions, I know which session is associated to Thorny, on some other associated to Dolly, and there are some other machines where I will eventually need to work. So I create sessions and windows for them, and I could be working on that here on this laptop. I have another desktop machine. I just continue working on that machine, and everything is preserved. Just to show you how that works, imagine that I'm here on this one. And let me see on this one. Just to show you what happens when you work on one session, because I'm sharing the entire screen, yes. Just to show you, imagine that this is one computer, and this could be perfectly another computer. So this is, I'm working here on a laptop, and whatever I'm doing here is reflected on both sides. So all the commands that I'm doing here on this computer are happening on Thorny. Actually, Thorny is keeping track of the content of those windows. I could be working here, I could stop working here, moving to the desktop computer, continue working there, and everything is preserved. So you will find this very good. To detach, there are two ways. If you just press Ctrl B D, you detach from the session. That this is one. And Ctrl B and uppercase D, you will look into the different sessions, and you can detach from them. Those are first, you detach from the current session and you return back to your normal terminal, your original terminal before the tmux, or B, uppercase D, show you the list of session available. And let me see if I am missing something here. Let me see. Space. Okay. Okay, you can put names to the sessions. And I think you can do it afterward. I think it's Control B, Control B. I think it's like this. Control B, $sign. No. What is the name? No. Okay. No, I think I covered everything. Okay. Yes. Now let's keep it like this. Do you have questions about this, about the other thing? It could be specific for your use case, for tmux, or for your research related to submission of jobs. I think I present what you really need to know, the bare minimum, for both things. If you want, you can search over the internet. There are like all the commands for tmux, the options. There are a few more things that are more obscure that are rarely used. Same thing for Slurm, and there are a few extra commands that maybe I can show you that, because there is one command that I never showed. There is this is a lock. This is a quick way of getting an interactive session. So if you want, this is number 6. This will be in command number 7. Let's say with 7 commands in the Slurp, you do everything that you want to do. And with those commands that I show you for tmux, you do everything that you want to do for the tmux session. So the windows, the sessions, the windows, and the panes, you keep all that. Anything else?
Hi, can you hear me?
Yes, I can hear you.
Okay, I'm still like confused that you said like, okay, we keep some like jobs running on the terminal in our laptop, but like if we close our laptop, then that might go away. So to avoid that, so we use tmux, or I was confused with that.
Okay, let me answer that both things. Let's say from
Okay.
the Slurp perspective, from the Slurp perspective, you have 2 ways ways of executing on the cluster. The interactive session, which allow you to enter commands and waiting, like working on your computer. You interact with the command. Imagine here. So let's say I will be doing. I start here. I will show you the entire interactive session from the terminal point of view, regardless of Tmux, nothing. So it's a lock. So it's this. So I will wait in a few seconds and I will be landing on one compute node. It takes, let's say, a few seconds. Well, once I land on that, I am operating one of the compute nodes. And it's taking a little bit. I could be loading Python, open IPython, start working on commands or doing something there. Okay, I got it. So module, this is an entire section. Model purge. So I clean all the modules. I will be loading lang, GCC 12, and lang, Python, CPython 11. So I have Python 3 now enabled on mine. And I can start running IPython, for example, and executing a script, or if I have, let's say, the Python script, I can execute this. I'm still running an interactive session. If I am using a normal terminal on your computer, you are using PuTTY or you are using Mobile Extern, a normal terminal, and you close your computer, this session will be disconnecting from Thorny, and your job will be killed. That's the first thing. How you avoid that? Well, first, if you are really executing something that is taking hours, you don't do it interactively. That's the first thing. The first thing is not doing interactively. Instead of that, use a submission script. You prepare the script, you know that this will run for hours. You submit the script, and that will be executed regardless of your connection to the terminal. So it's not using your terminal or all that. Another way, if you want still to run something interactive, but for example, you are checking for something that will take like 30 minutes, 1 hour, and you are afraid of losing your interactive job, what you can do is a combination of launching the interactive job from Tmux, so opening Tmux, launching an interactive session there, and you execute the command that will take 30 minutes. You go take a coffee, drink some tea or something, wait, and after you decide to execute another command and playing with that. But you are protected from this connection because it's running behind Tmux. That's another way of doing things. When you really need the interactivity, but it's not so short time, the time lapses between you execute commands, that you want to preserve the session for. See, if by any chance the computer went asleep and you got disconnected, you just reconnect. Let's say I'm here. Imagine that I detach. I'm still running there. I am detached. I will be leaving entirely. So I will be closing. Oh, we're closing the terminal. It's like going home and doing something else. Let me see here. I will be making a little bit bigger here. So I will be reconnecting to Thorny. I will be asking for my password. Now the duo. Going into Thorny. And I reattach my session, and I still running here on this machine, and mm, my IPython execution is there. I'm not losing that. So it's a combination of the things. From the point of view as learn, you either execute interactively or non-interactively. Most of the time, for real purposes, you execute non-interactively. You create some script that will run for hours, days, and you submit that script. You submit many scripts. You submit to the machine, and you don't care when it starts, when it finishes. You just want to get the job done, and you will not be interacting with that. They will not asking for anything. The computer knows what to do via the script, what to do from the very beginning to the very end. That's one thing. However, when you are learning what to do, when you are exploring the commands that you want to do, or you are doing at the scaled down version of your simulation, sometimes that helps. You want to do something really, really big, but you want to test if the parameters are good or not. You try with something small, something that runs faster. At that moment, it's a good idea to run interactively. Do, check, execute, see if that is working, try with that something else, see if you gain some performance by tweaking this parameter, changing this here and there. That's the reason, that's the real reason why you want to work interactively, for testing, for exploring the things that you have to do to your code, for making it work. And for that, if you really want to use something like this from a terminal, and you want to survive the unfortunate circumstance that the computer won't sleep, which happens a lot because on a laptop, they try to preserve energy. So after 5 minutes, the machine could send to sleep. They will disconnect from the network, so you could be losing your session. However, if you are using Tmux is protecting you from those cases, because the terminal is actually living on Thorny on the login node, and if you reattach, you can continue, start executing commands, and everything is fine. That's the idea. It's a combination of both things that allow you to work interactively and still preserving your session. That answer your question?
Yeah, that answered my question. Yeah, thank you.
Okay, perfect.
And I have a separate question, like,
Yeah.
so I don't know if that is how the things work here. So for
Mhm.
example, if I like log into the like machine, and if I just don't do anything and keep it idle for like a while, then like it seems to freeze. So is it like by default like that, or like?
Well, there are several things here, and yes. So when you connect to that is my experience, and that's why I also use that. This is like a hidden reason why I also always use Tmux. You first need to connect to the SSH gateway, which is a machine that we don't control. So we means research computing, the division where I belong. We manage the clusters, but we are not part of ITS. We are a separate entity, and we have no control on the SSH gateway. The SSH gateway, they have a mechanism for checking if you are idle. If nothing is happening on the session, it'll kick you out. So for me, Tmux is a way of bypassing that from the point of view of the SSH gateway, because the session is permanently changing. If you see, at least on the bottom, I have the hour, they have the timing, and at least that is changing every minute. So the terminal is changing, and it's sending that to my screen, and it noticed that the session is active somehow, and the SSH gateway is not kicking me out. That's so what is kicking you out from it is the SSH gateway, in fact.
Oh, okay.
There are some other things. Let's say we have things like that, like timers for killing sessions for administrative accounts. Let's say we don't want an administrative account like the super user account to remain active forever. It's a security issue. So on those particular accounts, yes, they have timers, and they will keep the session after a certain amount of time. But in your case, as a normal user, in your case, is the SSH gateway, which is cutting the connection because it's noticing, for example, that you did nothing in the last, the terminal have not received any update in the last 5 minutes or 3 minutes. I don't remember exactly. When you connect to the, let me see if you see here. When you connect to the session, I think they mentioned that, but I'm not super sure if they in the message of the day they mentioned that. Well, they put 8 hours, but in my experience, it's not 8 hours. It's like 8 minutes.
Yeah, exactly.
It's a few minutes, and if nothing happens, it freeze, or like you mentioned, it depends on the terminal, on the terminal that you use, or the SSH client. It frees you entirely, so it means that you start hitting the enter and nothing happens. So you actually are disconnected, and at the end, it kicks you out, and you get back your prompt on your script. But it is the SSH gateway which is doing those things, which makes sense for them. That makes sense because they are concerned about the security, and someone, if someone leaves the computer active, someone could enter and very quickly get access, and if they know what to do, they can escalate privileges. So and someone else will be blamed for that. So I understand why they do that.
Okay.
If you know what you are doing, okay, Tmax is kind of protecting you from those, and there is nothing bad with using Tmax. And
Okay.
that's why it's very convenient to have it, even if you are planning to use just one terminal. It's still worth it.
Okay. I got why was the
Another thing that I
problem.
do,
Okay.
this is a time-saving skill, let's say, is on this machine. This is right now I am on the SSH gateway. So what I have is here on my basher C, I have some aliases. So I connect very often to machines. So I have some aliases here. So you notice that I don't tie the whole thing. So I have an alias SSHTF, and I go to Thorny. SSHDS, I don't go to Dolly Sots. And I can go to 2 different machines on Dolly Sots. So I have DS and DS2. So I have quick aliases that allow me to jump very quickly to the cluster, and here, yes, Tmax A, and I can move around um, with Tmax with the different sessions. I don't know where here. And you see here, I am recreate the session and all that, and it's still working here. So I have my 4 hours. I just execute the command salloc, and I never put any other extra argument. So I'm getting 1 node, 1 core, using the default partition, so standby. So this will be preserved for 4 hours. And at the end, yes, it will be slurred. It will be the cluster, which will kill the IPython session, the IPython terminal here. But that's a different story. Okay.
Okay. Thank you.
Okay. Anything else? Any other question? we have some time here for question related to your things that you would like to see related to your research, particular cases. Because with this, we kind of close what we would like to present you for the general usage of the cluster. So
I have one more question. So do we need some kind of authorization to connect to Dolly source? Because I can connect to Thorny-Flat, but I could not connect to Dolly source.
okay, so yes, not authorization. You need a different account. And so when you request your account, it will the first time it will. I don't know how old are you in the cluster, but the first time that you request the account, you mark which cluster do you want to connect, because each cluster is a different account. So probably you only have an account for Thorny. It's just going into the help desk, open a ticket for getting an account on the other cluster, on Dolly source, and you get it. Same thing. You fill the form, you mention the PI, all that, and you get an account on Dolly. Those are two different accounts. They're two different home folders, two different Scratch folders, but still you can jump between one cluster and the other. So that's what I'm doing here. For example, let me see here. Oh, well, not that. Let me see. Oh, well, here, maybe for example, here. So I have my way to working on Dolly, and also I don't know if that probably is that not by default, but it's something that I do that I can show you. This is not bad thing. How I jump between the two machines without having to answer passwords or things like that. This is convenient. It is this command. There are two commands involved. Keygen here, SSH-keygen. With this, it will create a part of files which represent the public and private keys. I will not execute that, but if you execute you will get here inside SSH files like this. File like this, which is the private key, and a file like this, which is the public key. So with this, what you do is SSH minus copy ID. You select the key that you want to use, the public key, and the machine where you want to use HPC, WVU. And with this, let me see, we'll try to copy. It will say that I already have that. They already exist. But this is the trick. There's two things. One, the creation of the key with SSH keygen. You probably don't need this. I think that all users already have pre-created the key. I'm not really sure. But in case that you don't have it, well, it doesn't hurt. This is first you create a key, and it will try to create a key there. And the second command, it will be something like this. Well, in this case, for Dolly here, for Dolly. And it will normally will ask for the password, and it will copy the public key into the authorized keys of the other machine. And the next time you can jump between the two clusters with no passwords involved, and that's very convenient too. And that's also what I do on the SSH gateway to save me all time on that. I also jump in from the SSH gateway to the cluster without passwords, and from the SSH gateway to Dolly, to Dorney and Dolly without password. Those are things that work. Let me see what I have here. Oh, okay. Well, Michael, for you have a question here on the let me see. Yeah. Okay. On this. Okay. You want to request GPU. So let me see. Let me go here. Okay. I will I will answer that question, which is basically the same on both clusters, but this gives me the opportunity to show you dolly sorts. Dolly sorts, if you execute something like this, we have one community partition. Oh no, community no. We eliminate that. We have the default partition is all the machines on Dolly, they have GPUs. They have A30s, A40s, and A100s. And so by default, you can request a job, interactive or non-interactive, up to for 2 days. That is the default. The non-default, the alternative to that is a partition for 7 days execution. That's one thing. For requesting GPUs, that is something important. There are several commands that you can apply. Let me see if I can show you here. I have one or created for that. There are several things that you can do. Oh, well, maybe this dumb job. Maybe this. Well, this is a very simple way of doing it. Let me see. I will not do this so extreme. So with this option here, you can request a certain number of GPUs. There is only, let me see, most of the machines on Dolly, this is for Dolly, they have 4 GPUs per node. So some machines, they have 4 A30s. Some other machines, they have 4 A40s. And I think the case for the 8 are the machines for A100. But I will not go that extreme. Let's see, I will be requesting 2 GPUs, and I don't care which GPU. And I will sleep for 60 seconds, and I would like to see the environment variables related to Slurm. So this is something simple to do, just for a quick job. So sbatch, same thing. The command is exactly the same. Let's see, SQ, everything works exactly the same. It's running on this particular compute node. By the way, on Dolly, there is a way with GPUs to partition a GPU such that you see that as a portion of a GPU. If you don't request anything special for the GPUs, a particular kind of GPU, you could be receiving one of those GPUs split, which is the case here. So I'm not declaring anything. I've just want 2 GPUs, and I will get those. I think this is still. Oh yes, 60 seconds. Okay. That's possibly the case that I'm getting. I will show you how that looks for the entire machine. So NVIDIA SMI will show you that this, I don't know how many, like this, all the GPUs have split it like in 4, I think, and this machine looks like having 16 GPUs. In any case, I think that, okay, no longer there. So I have here, okay, I think it's this one. Those are all the variables related to GPUs. Yeah, so what I'm doing here. Well, probably the script contains that. Let's see. I did something wrong here. What GPU? No, yes, I think I did something wrong here. Oh, oh, a typo here. Is sbatch. Now it's okay. Well, let's try to do it smaller, 6 seconds, because what I would like to see is the effect of the GPUs. So S batch. So the only thing that you have to do is to put, I have a typo, so is this sharp S batch and the number of GPUs. As simple as that. There are some other ways, and I will show you that, how you can declare very specifically which kind of GPU do you want. Because the different GPUs, for example, on Thorny, the P6000s and the RTX 6000, they have 24 gigabytes of GPU RAM, while the A100, they have like 40 gigabytes. Sometimes people really need the 40 gigabytes. So the RTX 6000, and also they do not perform as well as the A100. So people that really need the A100, they can specify, I just want to run on the A100. And I will show you how to do that. Let me see if this is, oh, this is out. Okay, let's learn this here. So you see here the machine where I was running. This machine and the number of GPUs. So let me see how this looks. I will execute this. And I will go to Thorny and show you how that works in the case of Thorny. So let me see. I could execute this via SMI. Okay. So let me review this. No, but where is that thing? I don't remember, so I will look into the manual. Okay. Okay, this is okay. This is how you do it. I will copy this. This is the real trick. Well, okay. So I will go again this one, and instead of this, I will be requesting, let's say, the A100. So GPUs A100 and 2 GPUs. So in this case, I am declaring oh, no, it's not like this. Gress equal GPU column A100 and the number of GPUs that you are requesting, and not this. Sleeping for 6 seconds, you will see all the variables, and you will see the output of NVIDIA SMI. So here, here, and if I do X batch, what is that? Let me see the logs. Because I don't. I will find. Mm. Let me see. Where is this? No. No. Okay. Well, I will show you on Thorny, and I will later look into the same file on Dolly. So in the case of Thorny, we have defined three different machines here. So the P6000, the RTX 6000, and the A100. So those are the types of machines that we have. So if we want to do something with them, let me see first, which the GPU for that, the GPU partitions for that are the GPU community GPU Inter or the community GPU weak, any of those. How they are right now? Okay, I think I can get this. So this is one of the things that I would like to use here. Being, let's use the sleep case here. So, okay. So here I change the partition to this one. Here I will be asking for this arch minus grass equal to GPU, let's say RTX 6000, 2 GPUs. I will be sleeping for 12 seconds. I will be executing this, and I will be executing the command NVIDIA SM to check in which GPUs I got there. So that is all that I need. I can submit this. Why not? Maybe it's this. Community. Week only. Missing some. What is that? Here I have that. Um, mm, okay. Oh, okay. Okay, the name is like this. Mm, okay. Okay, what's my is this is the name of that. Okay. is here. Like this. I think it was like NVIDIA. It's there. That's fast. No, exactly. Okay, that is the name I was confused. So this is the idea. If you want to request a specific GPUs on Dolly and Thorny, the name there is different. You put something like this: dispatch -- grass GPU, and here the name is like this: NVIDIA _ A30 or NVIDIA _ A40 or NVIDIA _ A100 for the different GPUs there. And when you get this 668, well, it will be like this. Let me see if I can expand this. Okay, you see here all the commands. The NVIDIA SMI will show you only 2 GPUs here. And the commands here for the variables, it will show you GPUs 0 and 1, GPUs on node just 2. Even if the machine has 4 GPUs, it will show you the correct list. And if you are using, for example, PyTorch, TensorFlow, and all that, those packages will see the 2 GPUs, just those 2 GPUs, regardless of the number of GPUs on the machine. Yes, so I will show you the names because they were hidden. Or there are probably ways to get that, but from the administrator point of view, that's what I was trying to think about. So share software, slurp, etc, and slurp the slurp configuration, which was what was looking for. So here you see. Let me see if I can stretch this a little bit. So here is a description of the nodes on the cluster. So this is how you actually configure the nodes. And what I was looking for, or was trying to search everywhere, were the different names declared for the GPUs. So in that case, it's NVIDIA A30. If you want to get a real GPU, an entire card, the A30, and there is a maximum of 4 per node, or NVIDIA _ A40, and there is a maximum of 4 per node. Those are the machines. This is the range of machines that are hosting those GPUs, and there are just a couple of machines, those two, the 35, 36, and they have 8 NVIDIA A100s. So those are, and for some reasons, especially in machine learning, also in molecular dynamics, some codes can use multiple GPUs. And for that reason, those are put together, and those have like 40 gigabytes. So there is probably another way of doing that. Is info -end, let me see, yes, hoc 035. To see all the variables for the grass. Well, I did it in the administrative way. So looking into the configuration file, which is the ultimate information for that. And there is another machine, but this is kind of a private machine where they have H100s, which is Those are the NVIDIA H100. They have 7 right now, because that machine has an issue. But originally they should be 8 NVIDIA H100s, which are newer than. In the case, let's see, let's go. This is for Thorny. So if you want to see, this is the location. This is the location for the configuration file. In the case of Thorny, let me see, let's go back. Right, let's go here. All that is in OPT admin. I think I need to learn to is here or is in OPTS learn. PTS learn, etc, and grass. This is where those are declared. Now, why? Let's learn how they are declared. Oh yeah, it's possible that I don't have the ability to do the same grass here. That's why it's not working. Because in general, those are the same machines. So that all P6000 or the PX6000, they have exactly the same amount of memory. Something else? Anything else that you want to see? But I think that we covered everything that. So next Friday, this afternoon, we will be talking about partial differential equations with Irene. She will explain about that. And Friday, it's for machine learning and deep learning. So for those who are not interested in that, this will be closing the most general side of what you need to know for using the clusters. Okay, perfect. Thank you very much, and see you this afternoon, 2 o'clock, or Friday in the morning, 9 a.m. for the last session. Thank you. Oh,